This is Colin Selleck of Binghamton University. This video lecture is on Chapter 1 from the book Statics by R.C. Hibbeler, and the topic is General Principles. Today's objectives are to provide an introduction to the basic quantities and idealizations of mechanics, to give a statement of Newton's laws of motion, to review the principles for applying the SI system of units, to examine the standard procedures for performing numerical calculations, and to present a general guide for solving problems. I'm going to cover what is mechanics, the systems of units, numerical calculations, and problem-solving strategy. So what is mechanics? Mechanics is a branch of the physical sciences that is concerned with the state of rest or motion of bodies that are subjected to the action of forces. Now, in general, this subject can be subdivided into three broad categories: rigid body mechanics, deformable body mechanics, and fluid mechanics. In this book, we will study rigid body mechanics since it is a basic requirement for the study of the mechanics of deformable bodies and the mechanics of fluids. Furthermore, rigid body mechanics is essential for the design and analysis of many types of structural members, mechanical components, or electrical devices encountered in engineering. Rigid body mechanics is subdivided into two areas: statics and dynamics. Statics deals with the equilibrium of bodies, that is, those that are either at rest or move with a constant velocity, whereas dynamics is concerned with the accelerated motion of bodies. We can consider statics as a special case of dynamics in which the acceleration is zero. However, statics deserves a separate treatment in engineering education, since many objects are designed with the intention that they remain in equilibrium. Before we begin our study of engineering mechanics, it's important to understand the meaning of certain fundamental concepts and principles, and I hope that this is a review for you. You should have gotten most of this in physics. So the following four quantities are used throughout mechanics. Length. Now, length is used to locate the position of a point in space and thereby describe the size of a physical system. Once a standard unit of length is defined, one can then use it to define distances and geometric properties of a body as multiples of this unit. And then there's time. Time is conceived as a succession of events. Although the principle of statics are time independent, this quantity plays an important role in the study of dynamics. We have mass. Mass is a measure of a quantity of matter that is used to compare the action of one body with that of the other. This property manifests itself as a gravitational attraction between the two bodies and provides a measure of the resistance of matter to a change in velocity. And finally, we have force. In general, force is considered as a push or pull exerted by one body on another. This interaction can occur when there is a direct contact between the bodies, such as a person pushing on a wall, or it can occur through a distance when the bodies are physically separated. Examples of this latter type include gravitational, electrical, and magnetic forces. In general, in any case, a force is completely characterized by its magnitude, direction, and point of application. Now, models or idealizations are used in mechanics in order to simplify applications of the theory. Here we would consider three important idealizations. The first is a particle. A particle has a mass, but a size that can be neglected. In this instance, the particle is the ring. For example, also, the size of the Earth is insignificant compared to the size of its orbit, and therefore the Earth can be modeled as a particle when studying orbital motion. When a body is idealized as a particle, the principles of mechanics reduce to a rather simplified form, since the geometry of the body will not be involved in the analysis of the problem. Now contrast that with a rigid body, as seen here in this railroad wheel. A rigid body can be considered as a combination of a large number of particles in which all the particles remained at a fixed distance from one another, both before and after applying a load. This model is important because the body's shape does not change when a load is applied, and so we do not have to consider the type of material from which the body is made. In most cases, the actual deformations occurring in structures, machines, mechanisms, and the like are relatively small, and the rigid body assumption is suitable for analysis. And also we have a concentrated force indicated by the white arrow. A concentrated force represents the effect of a loading which is assumed to act at a point on a body. We can represent a load by a concentrated force, provided the area over which the load applied is very small compared to the overall size of the body. An example would be the contact force between this railroad wheel and the rail. Now I'd like to talk about Newton's three laws of motion. Engineering mechanics is formulated on the basis of these three laws of motion, the validity of which is based on experimental observation. These laws apply to the motion of a particle as measured from a non-accelerating reference frame. They may be briefly stated as follows. The first law: a particle originally at rest or moving in a straight line with constant velocity tends to remain in this state provided the particle is not subjected to any unbalanced forces. So as long as the sum of these forces is zero, there will be no change in the velocity of this object. Now the second law: a particle acted upon by an unbalanced force experiences an acceleration A that has the same direction as the force and a magnitude that is directly proportional to the force. If the force is applied to a particle of mass m, this law may be expressed mathematically as force is equal to mass times acceleration. And the third law: the mutual action of and reaction, the mutual forces of action and reaction between two particles are equal, opposite, and collinear. Now collinear just means it happens along a line. Now let's talk about unit systems. The four basic quantities, length, time, mass, and force, are not all independent from one another. In fact, they are related to Newton's second law of motion, F equal ma. Because of this, the units are used to measure these quantities cannot all be selected arbitrarily. The equality F equal ma is maintained only if three of the force units, called base units, are defined, and the fourth unit is derived from this equation. Now, SI units, this is the globally accepted standard. It's the International System of Units, abbreviated SI. It's a modern version of the metric system which has received worldwide recognition, as I said. As shown in this table, the SI system defines length in meters, time in seconds, and mass in kilograms. The unit of force, Newton, is derived from those three quantities. And here you see the abbreviation for each of those quantities. Now this unit of force is called a Newton, and it is derived from F equal ma. Thus 1 Newton is equal to the force required to give a 1 kilogram of mass and acceleration of 1 meter per second squared. Now the second system is the U.S. customary system of units. I like to call it FPS for foot, pound, second. Those are the units used in that system. In that system, length is measured in feet, time is in seconds, and force is in pounds. Now in this system, the slug is the derived unit, and it is a unit of mass. A lot of errors are made working in this system, FPS, because when you see mass, a lot of people plug in the weight and not the actual mass in slugs. And those are related by, of course, the weight is equal to gravitational acceleration times the mass. Now, sometimes we convert units from one system to another. We're not going to do much of this, but if you have a pound, for instance, in FPS system, that's equal to 4.448 newtons. And the conversion factors for all of these can be looked up online. Now, prefixes. So, when a numerical quantity is either very large or very small, the units used to define its size may be modified by using a prefix. Now, some of the prefixes used in the SI system are shown in this table here. Each represents a multiple or submultiple of a unit. And if applied successfully, it moves the decimal point of a numerical quantity to every third place. Now, here's some rules for use when using the various SI symbols. First of all, no plurals. We don't want to see 5 kgs. That's confusing. It might mean kilogram second, right? Quantities defined in several units which are multiples of one another are separated by a dot to avoid confusion. So you see that here. It's meter second, so you put a dot in between the two. Otherwise, if you didn't, it might be confused for millisecond. Most symbols are in lowercase except for these: Newton, Pascal, mega, and giga. The exponential power on a unit having a prefix refers to both the unit and its prefix. So if you're going to have centimeters times centimeters, that is centimeters squared. Now, in general, avoid putting prefixes in the denominators of compound units. Don't write newtons per millimeter, but rather kilonewtons per meter. And the table in the textbook shows the prefixes used for all of these, for the SI system. Now, when you're doing numerical calculations, numerical work in engineering practice is most often performed by using handheld calculators in computers. It is important, however, that the answers to any problem be reported with justifiable accuracy using appropriate significant figures. And I will be grading on this, so pay attention. In this section, we will discuss these topics. Now, the first is dimensional homogeneity. The terms of any equation used to describe a physical process must all have the same units. So, for instance, if you have, you probably know this one: velocity is equal to, distance is equal to velocity times time plus 1/2. The acceleration times time squared. Well, each of these terms in this equation all have to have the same units. And in this case, of course, it would be meters. Velocity is in meters per second times time in seconds. Meters over seconds times seconds is meters. And I'll leave it to you to make sure that 1/2 AT squared is also has the units of meters. I used a significant number of significant figures, 3 for the answer and 4 for intermediate calculations. The reason to use 4 for the intermediate calculations is so that you don't have round-off error. And most of you are using calculators anyway, and they'll keep that precision for you. But the important thing is when you report the answer, write it down, tell someone what the answer is. You can only use the right number of significant figures because that tells you how accurately that measurement is or that calculation is. And then lastly, be consistent when rounding off. I just say when greater than or equal to 5, round up. So this 8 is greater than 5, so we'll round that up to 3530. Smaller than 5, that 1 is less than 5, so I'll round it down. Now, here's some problem-solving strategy tips. It's important to always present the work in a logical and orderly manner as suggested by the following sequence of steps. Read the problem carefully and try to correlate the actual physical situation with the theory studied. Tabulate the problem data and draw to a large scale any necessary diagrams, and please draw large. Makes it so much easier to read. Tabulate the problem data, already said that, and apply the relevant principles, generally in mathematical form. When writing any equations, be sure they are dimensionally homogeneous. Then solve the necessary equations and report the answer with no more than 3 significant figures. Study the answer with technical judgment and common sense to determine whether or not it seems reasonable. Now, I'd like to cover some important points that start to summarize this lecture. Statics is the study of bodies that are at rest or move with constant velocity. A particle has a mass, but a size that can be neglected, and a rigid body does not deform under a load. That's only in statics, by the way. A force is considered as a push or pull of one body on another. Concentrated forces are assumed to act at a single point on a body. Newton's 3 laws of motion should be memorized. Mass is a measure of a quantity of matter that does not change from one location to another. Weight refers to the gravitational attraction of the Earth on a body or a quantity of mass. Its magnitude depends upon the elevation at which the mass is located. However, we won't worry about that in this class. Typically, we use G is equal to 9.81 meters per second squared, or 32.2 feet per second squared. In the SI system, the unit of force, the Newton, is a derived unit. The meter, second, and kilogram are base units. We use prefixes to represent large and small numerical quantities. The exponential size should be known along with the rules for using the SI units. We want to perform numerical calculations with several significant figures and then report the final answer to 3 significant figures. Algebraic manipulations of an equation can be checked in part by verifying that the equation remains dimensionally homogeneous. And finally, know the rules for rounding off numbers. This concludes Chapter 1, General Principles of Statics by R.C. Hibbeler. The next video in this series is Chapters 2.1 through 2.4, Force Vector Operations. See you in cyberspace.